times UTT. That's the chain rule, correct? Right? First you bring the 2 down, cancel that 2, and then you take the derivative of what's inside. So what was inside was UT, so you're taking the time derivative, so you're taking another time derivative. Okay. Same thing here, you have T, UX, and then what do you put here? What if I take the derivative of the inside and I get a UXT, a mixed derivative. Okay, good. All right. Oh, I forgot my row here. There we go. So UTT, well, that's actually, well, we know. So I have to give you, that U satisfies the wave equation. Right? So that means where I see a UTT, I can put a C squared UXX. Correct? So where I see one of those, I can put one of those in its place. Okay. Another thing I can do is note that C squared is actually T over rho, right? That's by definition. All right, so we'll do that. And then we have a rho times C squared. So what does that become? What is rho times C squared? This is T. We like, right? And now, because what's nice is now both my terms are the same factor in front of them. They both have T in front of them. So I can actually move the T outside. Okay. So what we can do now is, well, here's what we usually typically do is, I'm looking at this and I see there's a double x there, so I can do a partial derivative of it. So I'm going to do a little, I'm going to do a little integration by parts, right? So I go ut ux, right? I take the antiderivative of uxx, I get ux, right? And I evaluate it at 0 to L minus integral of 0 to L ut, and then I put a spatial derivative there, and add that ux, right? dx, and then a plus. Okay, but by Clairaut's theorem, right? We assume that U is smooth and continuous and all that, so partials, the order doesn't matter, right? Provided we have smoothness. Right? So what does that mean about this and that? They're the same, right? So they cancel. And the answer is okay. So now boundary conditions. Another important fact that's necessary for this is boundary conditions. So let's just go with 6 then. Alright, so that's U. So U of x, at 0, comma c is equal to 0, and U at L, comma c is 0. All right, what about this then? So I can actually evaluate that as c at U at 0, L, comma c, that's ut, ux, L, comma c, minus ut at 0, comma c, u x at 0, comma c. All right. Well, what does this mean here? So that means it's fixed for every time it doesn't change, right? It's always 0. So what about ut at 0 and L? Fixed means does not change. ut at 0 or L, comma t, is also 0. Right? I mean, if you have fixed strings, the derivatives, the time derivatives of position on the ends are not changing by definition. Right? So what does that mean about this whole thing here? 0, right? So in a fixed string with no friction or anything like that, the time derivative of energy never changes. It's always 0. Energy might change form from potential to kinetic, but you never lose anything. Energy is conserved. So we've done this calculation previously, but I think everyone is a little blown away at the time. I think actually you guys did a homework problem on this. Okay. So I just wanted to go over that again. But yeah, we could add friction, right? Should we do that? Where would we add friction? Okay, let's see about adding friction. Here's where I was, right? So dV dt was equal to 0 to L, and then we had a rho ut plus t ux t ux. Okay, there's a 1/2 out. No, the 1/2 went away. All right. So now tt is equal to c squared uxx minus something k dt. Right, so anywhere I see one of these, instead of just putting that in its place, I put this whole thing in its place, right? I have more swapping to do. So we have that same term, t ut uxx, right? But then we have this extra one here, we have a minus, we have a rho times k ut quantity squared, right? Because anywhere I see one of these, I'm putting this in its place, and it's multiplied by rho ut, so I get a ut quantity squared. Okay?
Where does the 1/2 go?
When you take the derivative, right, because there's a square, when you're doing the chain, you see power 2 comes down, the 1/2 goes away.
Okay.
So always, kinetic energy is always 1/2 mv squared.
Mm-hmm.
Right. And the potential energy in this particular case also has a 1/2 in it. So there we go. And then we also have plus t ux uxt tx. Right, so we already knew what happened to this term, right? When you put those together, you get exactly this thing right here. ut ux. Then you have this term here. But let's again go with a fixed end condition here. If I put a fixed end condition in here, this becomes 0 again, right? So what I'm left with is this. dE dt. Time rate of change of energy is negative rho K 0 to L times. Oh, did I put 2 K's in there? Should have done that. Square. dx. Alright, so while we're at it, so so here I might, I give you a problem way to do this, but I also give you a solution. So here, give a particular solution to the equation. So this particular solution obviously is not a solution. That's a solution to the regular wave equation, PD. So let's find a solution to the friction one. Should we do that? Do a little separation of variables? Done this before. All right, so we're going to change gears a bit. We'll come back to this problem of finding out what this is. How does energy dissipate when you add friction over the whole system? Well, let's actually find a particular solution. This is a simple one. Let's see where it goes. We're kind of doing a potpourri of problems today, right? I'm just kind of, I don't know. This is sort of air guitar math.
Now it's how it dissipates with friction.
Yeah, so now let's do a friction problem. So we'll do a separation of variables on friction. Okay, I'll find a solution for that, and then we'll plug it in and see what happens. Right? Well, how much energy is getting lost through over time? Okay, so again, we have u to c t is equal to c squared u x x minus k u t. And let's keep everything simple. I don't want to. We'll just set everything to 1, right? Just have a simple problem. Not clutter ourselves with parameters. So. All right, so there we go. Let's deal with this one. So, like always, u is equal to p times q, right? So it's going to be p of x, q of t. Right? So we have q double prime p is equal to p double prime q minus p times q single prime, right? Well, I'm going to collect up all the derivatives of q on one side, so we're going to have q double prime, put the p outside, plus q prime, right? Then we have a p double prime times q. Right? I just moved this over and factored out the p. So what we get, of course, is after separation. So let's do fixed end. A fixed end, let's say that u at x, we'll say L is going to be pi. I like that. This is always a nice one. It keeps the math a little cleaner. Okay. Let's go with u at x comma 0 will be just sine x, right? Let's try sine nx. I want to see what happens for different n values. Okay? Right? And that u prime of x comma 0, or sorry, u the time derivative of u, I'll just say that's always 0. So there's a particular problem I want to solve. Again, so I'm looking at different vibrating modes here. I want to know, how does energy dissipate for different modes? Because we're eventually going to plug in our answer back there. Okay? Alright, so we have to do this. So this problem, p double prime over p, well, we know this has to be the negative lambda, right? So, and we know how to solve this one, right? It's actually on your checklist. They put it on there that you can just immediately, pass go collect your $200, right? What do we know the answer to this one is? I won't actually give anyone $200.
Yes.
$200 in play Monopoly money. What is it going to be?
N cosine.
Okay. And so now we have our lambda. Now let's go back to the Q equation. We have Q double prime plus Q prime is equal to negative n squared times Q, because we multiply the Q over, right? So now we have a whole sequence of ODEs to solve in time derivative. Okay, so there's our linear ODE. Well, this is a linear ODE, so we're going to try very standard, find the characteristic equation, right? So our candidate has to be e to the RC type solution. So we get from that a characteristic equation of r squared plus r plus n squared is equal to 0. So what's the r value? Well, we'll just have to use, what's our favorite? Yeah, we'll have to use the quadratic, right? Because we're doing this as a function of all those n values, right? So r equals minus 1 plus or minus square root of 1 squared minus 4n squared all over 2. Is that right? Right. So this is for n is equal to 1, 2, 3, 4, and so on and so forth. Right? So negative 1/2 plus or minus. Right, for every value of n, what's that discriminant? What sign is it? Negative, right? So we got complex answers. So the answer is complex. So what we're going to have is an I, 4n squared minus 1, all over 2. Sometimes it's sometimes nice to put that 2 inside. Like that. So these are the vibrating frequencies of the system. So I would say, this is the decay. And then this is the oscillation frequency. So your RNs, because it really is a function of n, is always going to be negative 1/2 plus or minus I. I'm going to call those omega n's, right? These are the oscillation frequencies. There's one thing one does in EDs is they learn their ODEs. You learn your ODEs really well, right? So what we have here is the Q and T. Well, we have these two linearly independent solutions. I can write them down as complex exponentials, but what do we typically do? We can do a change of basis, right? A change of basis is to what? Sines and cosines, but with what twist now? Because it's complex, not just pure imaginary, it's complex.
Sinh and cosh.
Nope, not sinh and cosh. So, putting this all together, un of x times p is equal to pn of x times qn of c. Right? So we can write all that down. It's going to be sine nx e to the negative 1/2 c that stuff there. Okay? All right, so of course, the general solution. So when I say general solution, the general solution to a PDE will be U of x comma t, will be a linear combination of all of these. Okay? So I write it in this form. So that'd be a great answer. So, I think one of the things I see, I don't know if this is a terribly bad problem, but, I think sometimes when people are panicked, something, they'll just look on the equation sheet, the formula sheet in front, and say, oh, this is the wave equation? Okay, we'll just throw in the general solution to the wave equation. Well, usually I'm going to give you some twist. I'm not going to give you exactly the wave equation. I'll give you with friction, say, or something like that. So I'll want you to see how you can work with that curveball, right? Question?
Can you explain why it's e to the negative 1/2 t?
Here are our characteristic values here. So this part right here is what I call those frequencies, omega, and that's the imaginary part. And that's the 1/2, right? So this is non-trivial. It's non-trivial, and to really understand it, you need to really understand your vector spaces and the notion of linear independence. Okay? But the idea is that e to the RT, which is Qn, right? So really there's a plus. The solutions we can write this way, right? That's the most general, way we can write it, which turns out to be a e to the negative 1/2 plus omega I omega n comma t plus b e to the 1/2 minus I omega n. Okay. If I were to look at any one of these, though, I can use Euler's formula. Which is that if I have it e to the a plus I b, it's actually e to the a times cosine b plus I sine b. And so really it's plus or minus, so I can put a plus or minus there. So, of course, these are complex valued answers. We don't need complex values. We want a real answer, real value. So, you can always take a linear combination of these two basis solutions here and add them up and find the degrees of freedom within this whole set of solutions for A and B that only give you the real values, answers to them. And it turns out the vector space, a vector space linear independence properties. The alternate form is rather than having these two, you say Qn is equal to e to the negative 1/2 t cosine omega n t times a plus b e to the 1/2 t sine omega n. Okay. And so these, of course, are both real valued, whereas these things here are both complex valued. But you basically take the real parts of each and the pure imaginary parts of each, and you combine them together in the right ways, so that you maintain linear independence. and you can cover the span of all solutions intersected with the only ones that are real valued. Typically in Math 2250, you'll go through problems that make you do this. Most people do it without knowing they're doing it. Okay. They do the problem well, but they don't understand everything about it, so it usually takes a few times to going over this. But it's related to this idea here that if U and V are a basis for some vector space or subspace V, then U minus V, I'll call that W1, and W2 of U plus V. So W1 and W2 are also a basis. And that's essentially what you're doing. Is if you add them and subtract these two solutions, you get you can find yet another basis to span your set. Okay. And the idea of a general solution means that you found a coverage for all possible solutions. The functions that you found, when you actually add up all those, you create all these linear combinations, you actually yield every possible solution under the sun that one could possibly get for this PDE, and that's it. Okay. So now the levers of control then are just choosing all these coefficients. So now, to boil it down, we have a specific initial condition here. Let's try. All right, so what was it? Sine n s. Right. So what is a? Okay. So well, what I have to do is plug in t equals 0 here, right? See what happens. So what I get is I plug in a t there. So once I have the general solution, so of course on your exams, I'd love this. Make me have just warm feelings. If you write down a general solution, circle it, and say, hey guy, hey dude, general solution. But now I'm going to find just one of those. Out of that whole heaping pile of solutions, I'll find the one that you want. Okay? And what you do is you plug in the t. So of course, e to the t where t is 0 becomes a. Who knows? And then if I put a t equals 0 in here, I get a. And then what happens when I put a t 0 here? Nothing. So that's it, right? And then you go, well, what does an have to be then? 1. So an, I made a little bit of a notational slip here. I'm going to call that k. Okay? So it's not the same as the index. Okay? So an equals 1 when k is equal to n. An is 0 else. Okay? My cold came back. Who else got a summer cold? I hear a few like of the doses. I've got it too. So, and then what about the bn? Always 0. Always 0, right? We don't want any of those. All right, so our answer then is u of x comma t is going to be e to negative 1/2 t, and that's the twist, right? So we have that decaying term, and then we have a sign. So yeah, I'm going to just be notationally a little bit cleaner with k there. So let's put that back in. So that's my vibrating frequency, temporal frequency, right? Oh, that's sure. You're absolutely right. Okay, so here, I should say here, that's the spatial frequency. And here is a temporal frequency.
They're both K still? So they're both supposed to be K?
Yeah, because we're evaluating them at a particular K value. Right? But the decay term seems to be not dependent on K. Right? It just seems to always be negative 1/2. Yeah.
Well, why is BF equal to 0?
Because we stated here, and I didn't actually go over this as thoroughly as one could have, but we stated this is the case. The time derivative was 0. So if I take the derivative of our general solution, right, our cosine goes to a negative sign, and our sine goes to cosine times omega n. Right? Then we evaluate at 0, you expose all the bn, right? And then you set them all to 0. Yeah. So I didn't go through that maybe as thoroughly, but that's a good question. Okay. So there's a general solution. So we compute the energy of this thing. Right. Here's our rho. We have another notational train wreck here, a log down. I use K as an index, right? So here, this is the friction term. Maybe I'll call that mu. Right? So mu is friction term. Factor. And then I said that was equal to 1, right? And then rho was also equal to 1, right? Well, I'll just get rid of that. Right? Negative 1. So here's our, and now what I have to do is, to compute the energy, I have to take my u, take its time derivative, and plug it in. So the sine kx, that doesn't depend on time, so I can just, it's just a factor that stays up front. It's a constant with respect to time. And now I have sorry, that should be omega k, right?
Is that just the product rule?
That's the product rule, yeah. So there we go, right? You good? I think we're good. Alright, so I'm going to have to square this entire thing, so really this is a sine squared kx, right? And then all of this stuff is squared. Does that depend on x at all? You can actually bring it outside, right? So we're squaring it all, so this minus and that minus can't, they'll go away, right? So I can make this now 1/2. Well, let's have an e to the negative t over 2 minus 1/2. Or I'll just go plus, right, because the minuses go away. Cosine omega k t plus sine, or omega, we have that omega k there, right? Sine omega k. All quantity squared, right? What's this one? Do we know this one? So that's L over 2. So what's L in this case? Pi over 2, right? That's a negative pi over 2. And then we're going to square this. So we see this e to the negative t over 2. That becomes an e to the what? Negative t, right? And now we have to, so we have a 1/4 cosine squared omega k t, and then we also have a and then we have these cross terms, right? How many of these do we have? We have, so we multiply these together, we get 1/2, so 1/2 and 1/2 make a whole omega k. Alright, so that's about as far as I'm going to go with this. So clearly this thing oscillates a bit, right? This stuff is going to oscillate. This is elliptic. It's going to have a I should back off when I say that. But clearly overall, it's going to be decaying. That's going to squash it down. Right? So energy is leaving. Friction, right? But there's also these oscillating bits here. So that covers a bunch of wave equation things. I think that was pretty good to just go over lots of wave equation stuff. Anything else we would like to look at when you're looking at this list of these checklist items? Anything you guys would like to discuss in greater detail?
It's an. Oh, sorry. Go ahead.
I struggle with the two-dimensional.
Laplace equation.
Yeah, where it's the surfaces and.
Okay. Yeah, that's a good one. Okay, so let's do on a rectangular domain. Want to do that? Sure. Okay. So let's try a unit square. How do we do? Okay, we'll do a square of pi.
3150.
A square of pi. Okay. What's that?
He's saying, why do we always see pi and never cake in math? I said, become a famous mathematician, create a new number, and make a cake. And you can take the cake.
You have your cake and eat it too. I'm trying to think. There's probably something they call cake, actually. Look it up.
Hey, man, you got let's go down somewhere.
No, I don't.
Because I have a feeling that, this just sounds like something people are definitely going to joke around with. Okay. So we have this square of pi. Ha ha ha. And now we need non-homogeneous boundary conditions. So this is the type of problem this is where is it on the list? This would be number 19. Number 19 on the list on your checklist of things to know. Okay, so we have this. So we need non-homogeneous boundary conditions. So we need some sort of. So should we do? And there's two variants in this problem. There's a flux-related one, and then there's a zero temperature one. So let's try zero temperature for now. So I'll say that on this side here, u at I, y is equal to sine y. Right? We're going. So if I was going to draw this out on this here, look like that on that side, and you know it's going to kind of do this. Okay. And we're going to have it 0 on all the other three sides. Okay, so this is a simple-ish problem. Simple-ish Laplace equation problem. So again, solve for u such that let's find out what the answer to this problem is. As usual, u is equal to p times q. We're going to have a p double prime, so p double prime q plus q double prime p is equal to 0. You have a p double prime over p equals minus q double prime over q is equal to negative lambda. Alright, so of course I can multiply this whole thing by -1. It wouldn't change anything, right? And so where do you put the negative sign on p versus q? Yeah, it's up to you. But there are some judicious choices. If you kind of can see ahead, like you said, if you can see ahead, what you really want to do is make, in this case, I do want to make this one positive. Because, oh wait, no, actually, I don't. I want to go the other way. So let's look at this. I could write it this way, or because remember, lambda has yet to be determined, so it's an unknown constant. It can absorb any negative you multiply by it, right? It's fine. It's just once you've solved for something, you have to just be consistent from there on out. It's an unknown constant until you determine it, and then it's fixed. And then you have to keep whatever your convention was. Okay?
Couldn't you switch the sign to make lambda still be negative?
Yeah. So you can, again, it'll absorb everything. I should have done that there. Okay. So again, I made that positive or negative. I do it merely out of convenience. Right? So in this case, we have this problem. And the reason this is the better one And this is because we know that Q at 0 and Q at pi are both 0, right? And then these boundary conditions coupled with that ODE yield a very nice answer. So what's the answer? Q then?
The sine.
Fine, right?
Yeah.
Fine. And so Qn, what we find is, and we can immediately step to this problem, is Q of y is going to be sine of n y, right? For n equal 1, 2, 3, 4, forever. Alright, so now, and what is lambda then? Lambda n is going to be n squared. Okay. So now lambda n is fixed. It has a specific value. So now we have to be consistent elsewhere. So now we go to the p equation. I hope this is working for you. You made this doing problems at the board. We're happy with this. Yeah. It's nice to have, a full 2 weeks of review practice. You guys get one more on Wednesday, and then we'll go in and have an exam. You guys remember when your exam is? 7:30 in the morning, right? I gotta give you guys Dunkin' Donuts or something for coming out.
Yeah.
You said it, sorry.
I've done it before.
Nuts. It's a thing.
What does it cost me for Dunkin' Donuts? For 35 something people?
You get Munchkins. They're good. The Munchkins donut.
Oh, right. Yeah. No, that'd be cheap. Give you guys a Dunkin' Donut. I'll do it. If I have time. Okay. So we have now this equation. Now we have negative p double prime over p is equal to negative n squared, right? Or rather, p double prime over p is equal to n squared. Or rather, p double prime is equal to n squared p. And this has solutions Pn of x. I think another commonality of these problems is people forget their x's and y's in their equations. Easy to do. It's easy to forget which is p and q. And so, of course, to help you with that, we'll just first, keep that in your mind. This is all about organization, really. These problems have a really nice flow to them. It's noticing when they're different than the problems you solved before, and when they're all the same, right? And it really boils down to that. And that's the challenge of doing these things. It's just making sure you have all of your ducks in a row or your donut holes. I don't know. Okay. But this problem has what kind of solutions? A cinch, and x. I should actually do cosh, right? That's usually our. And then b cinch and x, right?
Sorry, where is it? Cinch and coach again.
The sign doesn't change.
Oh, because it's the positive. Okay.
Yeah.
Gotcha. Because when we have negative, sorry, when we have negative lambda, then it's the sines and cosines because it's the minus. All right.
But it's kind of like here. I had this thing where I was like, well, I could choose this or this, right? And one just happened to be a little more convenient for me, but either one works. There's another scenario that works just like that here, right? We've all been through this territory, but let's just go over it again. Okay? Or what? Was another set of linearly independent solutions What do I put here?
X minus L?
L minus X, in this case, pi minus X. You're exactly right. Just flip the sign. Okay. Right, so the question is, which one is more convenient for our problem? And it really depends on where that non-homogeneity is, right? So either one will work. You're fine either way. If you want me, I'll just do both of them for you, okay? Well, let's see. We have it on, so when I pick X equals L, so X equals pi, what happens? Well, this becomes what value? 1. Right. And then what does this become? 0. And that's really crisp. Okay? That sets up. So this is the one you want to choose. And the idea is the kind of general rule is to choose the L minus X version when the non-homogeneity is on a far side, I guess you'd say, far side. Because what do I mean by far side?
Towards the L.
Yeah. So I'll pick an X, L minus X or an H minus Y type thing if we have it on here or here, right? If we have non-homogeneous on these sides, you're going to choose this. It's better to choose this one. But if you choose either one, it works just fine. You just have a little bit more work involved figuring things out. Because I have this A and B. These A and B are free parameters. We've yet to determine them. But now let's do so. So, general solution. So once you find your P's and your Q's, you put them all together. So there are all the solutions. So in a lot of these problems, I'll even ask you, find the general solution, then find the particular. And what's good about that isn't that I'm making you do extra work. It's actually helping organize your work. By finding the general, it helps you find your particular. It's a very common place to trip over your shoelaces, so to speak. Is, you got your shoes on, you're ready to go, you did everything right, but forgot to tie them. So when you start going for the 100-meter dash, you just, cartwheel after that. So getting everything, and this is the sort of, to do more metaphors with you guys, this is getting your ducks in a row. Now you have everything, now find the one that you need, okay? This is everything. So, this is everything with a non-homogeneity on the X equals pi side. So now we go like this. What was it? We set it equal. equals pi, I get an an right there. Plus, what happens when I put x equals pi here? I get a
0.
And that's why it's nice. That's why we choose the pi minus x version, because it made that 0. Our linear algebra then can be very simple. Right? We still need to determine what the bn's are, but we'll do that in a second. Alright, so what are the ANs then in this case?
1.
1 with
One.
1.
And I really like, if I look on your previous midterms, people are really good at doing this now. Everyone knows exactly what to do when they get there. But the critical part is making sure you get the right thing here so that this works. But everyone's very good at doing that. Makes me happy. Right. We still have the bn's. So a lot of times people then stop though and they forget about the bn's. Right? But we still have those bn's. So the question then is now, what are the bn's? So now we have to evaluate on. So we've used this and this boundary condition to find my sine and y, right? And we've used this boundary condition here to find our non-homogeneity. We're going to use this one now to find the bn's. So now, if u of x comma y is equal to some oh, I should really put. Oh, I need to back up here. I'm forgetting. Times B1 plus okay. So we still have the B1 and all these other BNs to deal with, right? Okay. So now we put x equals 0. We know that's equal to 0, right? So the 0 in there, we get a sine y times cosh at pi, right? Plus b1 sine y. What happens when I put a 0 in there? I get a sinh pi, right? Plus the sum 2 to infinity bn okay, this whole thing has to be 0, right? We see these as a common factor of sine y, right? And so we need to get rid of everything with sine y. So what does b1 have to be?
1 over 2. Or 0.
Isn't sinh of pi 0?
No. Only 0. It only has 1 0 in the real one. So, what we see here is 0 is equal to sine 1 plus B1. Sorry, she's kind of coach pi plus B1 cinch pi. I'm just rewriting this actually. Clearly, this whole thing has to be 0, right? So the b ends equals 0 for n greater than or equal to 2. But to make this part 0, I have to make this 0. So what does b1 have to be? Negative cosh over cinch of pi. Okay. So now let's put this all together. Cosh pi minus x minus cosh of pi over cinch of pi times cinch of pi minus x. And that's the answer. Remember that cosh and cinch, they're essentially exponentials. They're just linear combinations of exponential solution. And they will, in fact, give you this kind of, it'll draw it this way. Like that. How much like that? Orthogonal projections, orthogonality, you guys are good at that. You guys, I think pretty much on the midterm, you guys just all got it right. Almost every, I mean, if you showed up, you got it right. Okay, but you can do that again, right? You know how to do that again, right? You're not going to forget it. This happens sometimes. Everyone gets it right on the midterm and they forget it on the final. Don't do that. Okay. All right. So, okay, good. Other questions?
I have question 5. Why is it split up into the different sections? Why is defaults? I couldn't figure out why.
Oh, question 5 on the practice.
On the practice.
Can I have a peek there? Yeah. But Dallin, you had a question too. I know you had a question before.
Yeah, him and I were talking. We were wondering if you could just briefly go over 27 through 29.
Okay. Can I look at this?
Yeah.
So you had which problem?
Just 5. Why D is false.
Right. Okay. This is a quick one.
Yeah.
This is the zero net flux property. It does not have the zero net flux property.
Oh, okay.
And so that's the short answer. Because flux out through a circle is always going to be a radial derivative. It's going to be related to the gradient. So if I have a disk like this, right? And if I have some surface above there, right? So remember, it's always going to be, the gradient is always going to be grad u dotted with the normal. And that's going to be times ds, and that's going to be a little flux element. Right? Or maybe d theta that helps because you're taking a little d theta there, going, okay. But the so it's going to be negative, right? Because it's always a negative gradient, right? But the idea is that this term right there, that reduces to the radial derivative. Okay. In this case, that was equal to, when I put the negative sign on there, was it sine theta? Right, but that doesn't integrate to 0. So the net flux isn't 0.
Okay.
Okay, so now 20, what now?
27 through 21.
27 through 20.
You mean on the review?
On the
Things
review,
in, things in
I'm
our
sorry,
sheet.
yeah, on the review, just trying to-
There you go. Thanks. Oh yeah, okay, so 29. Alright, so I'm really going to start at 26. I think this is a good spot to. This is on the checklist, yeah. So maybe it'd be good on Wednesday. I'll make up a bunch more problems of these, and we'll all do them together. I think Fourier transforms probably where more of your energy should focus there, right? Okay. So, I don't know, let's just do a quick one. Heat equation with decay. Alright, let's call it diffusion. And degradation. So we're going to have U at x comma 0 is going to be just a delta functional. X, let's say we'll put it at 42, obviously. Okay. So we're going to drop some gunk at this point, and it's going to diffuse but also degrade. So D is equal to kappa uxx minus, we'll say, we'll call it C, well, I don't want to use C, call it beta, yeah, right? So this is your diffusion, I'll call that D for diffusion. D, that's your diffusion term, and this is your degradation term. Okay. And again, X in this case is the entire real line. Alright, so Fourier transform. Okay, so the Fourier transform of the time derivative is the time derivative of the transform. And the transform of a second spatial derivative is negative omega squared times the transform. And there goes through. Again, the Fourier transform is linear, so it passes right through sums and scalar multiplies and all that stuff, right? Alright, so this is now an ODE. We can solve this ODE.
He does, Will.
Yeah.
When you have minus beta U, is there a... Okay, never mind. I'm thinking of US, because UX would be like omega Right, minus omega, okay.
Yeah, so that would be an advection term there.
Okay.
We're talking about degradation now, so it's just minus u.
Okay.
And you can see that, right? You say, this is the amount of, so I'm looking at time derivative of u, right? So I think it's, one important thing I'd like you to get out of PDEs is be able to kind of decode what PDE is saying quickly. Just look at it and be like, okay, this is this type of physical thing with a little bit of this and this and this, right? So you look at this and go, okay, time derivative. So we're talking about a conservation type principle. How much stuff is growing or shrinking in this region has to do with some sort of dispersal due to diffusion. And there's also some degradation, right? There's a birth-death process. If I'm going to have, dy dt minus y, right? This is a decay type situation. Minus y. The rate of change is the negative of the amount you have. So this is a death type process. So if this were a diffusion, this is diffusion in a giant one-dimensional lake. But there's also basically little bacteria that are wandering around inside the lake, and they are going to eat whatever you're putting in it, right? And they're going to, through some sort of random, at the microscopic scale, it'll be random, right? That these bacteria will run into a piece of, cow manure and gobble it up. The chances that they're going to be able to do that, to actually run into a piece of cow manure and gobble it up, it's a random thing, but the idea is it should be proportional to the amount that's there, right? Right, and that's why it's always negative beta u, right? And so this is derived pretty rigorously in Math 2250. I won't belabor that now. The long and the short is now that in the transform case, though, we get an ODE. Okay. I can call that something else if I want. I'll call it capital. Lambda. So, U. Okay, and there's always a constant that goes out front. Okay, so okay. So because we put a t equals 0 there, this is just going to be equal to a. But what in this case? I have an initial condition here, right? What is the Fourier transform of delta? What is that going to be? Right? All right, is it plus or minus?
Should be. Yeah, I think it's plus, yeah.
Yeah, it's plus. Divided by 2 pi. Right? The integral of any delta functional, you always just you just evaluate this function at 42. Plus the 2 pi.
Wait, so the top one you just solved it real quick in your head?
Yeah.
Okay. I want to make sure.
Yeah.
So if it was delta x plus 42, would it be negative I omega 42?
Yeah.
Yeah.
So the definition of the delta function, you can really think of this as the definition of the delta function. The delta function isn't actually a thing that spits out values. It is not actually a function. The definition of the delta function is only really understood in an integral. If C, D, So, that's my capital U. Now I have to find little u, right? I'm running out of chalk. What we have, yeah, we just write it like that. So what is that term again? It's going to be
omega squared plus beta.
So now we have to do a Fourier transform, inverse Fourier transform. That's what we do. And when we get to this, it's always about picking, is really factoring this thing into these factors and knowing what to do with each one. Okay? Each of the I 42 omega, we're going to use the shift theorem on that, right? Anytime you see something I omega, just a constant times I omega, think shift theorem. Anytime you see, what do you see here? We see a e to the negative beta t, e to the negative omega squared, e, e. Okay. First of all, this constant contains no omega in it. Right? So,
Did you intend that to be the Fourier transform of all that, or did you forget the inverse sign?
oh, sorry,
I
yeah.
was kind of lost there.
Nope.
I thought you were.
There you go.
Okay.
And this is equal to little u, right? This is what we want, is little u, right? I remember this is an integral, but this thing here does not depend on omega at all, so what do we do? Pull it out. It's neat how decay usually works this way, right? It just kind of comes out front. It just kills everything off. It's just a multiplicative factor, correct? Right. So here, this is, I'm going to do the shift. So what we do for the shift is if we call it G is equal to little g, then that's equal to g of x. This is going to equal to g of x minus 42. Anywhere I see an x here, I just put an x minus 42. Right. So the question then is,
okay.
what's this one? Should be on the list, right?
Oh yeah, that's gonna be
That's the Gauss
Yeah, it is Gaussian.
Oh, I forgot my 2 pi, right? 1 over 2 pi. It should be a 1 over 2 pi and everything. I always forget that.
Wait, is that just on the delta function term?
Yeah. I can put it there.
Technically, can't you pull it all the way out in front?
Yes. If I have my 2s and my 4s. At any rate, this is it. I have to evaluate it x minus 42 and multiply it by this e to the beta t on the outside. So my u of t, x comma t, is going to be e to the negative beta t times this whole thing. But we're going to divide by 2 pi, so we'll get rid of the 2 pi that's here. And now where there's an x, I put an x minus 42. Then I put my 2dt. Put a minus sign there. And there's the answer. Again, this thing. Yeah.
Sorry. The e to the negative I omega x that you had up there before you pulled the e negative beta t out.
Mm-hmm.
Is that one the part of the shift one? Is that where that one went? Because you have the e to the negative I omega x and then times the 3 other e terms.
Mm-hmm.
And then in the next one, you only have the
that e to the I omega x is part of the inverse Fourier transform.
But where did it go?
It's not multiplied by anything here. It's part of this f inverse. Because what I'm actually doing.
The definition of the f inverse is
Yeah.
Oh, okay.
Yeah. So what you see here that I never actually have to perform any integration.
Because you use
all the theorems.
Because I'm using a bunch of theorems to do the work for me. Now, if it's possible, I can actually go do all the integration. I don't advise that. It usually involves a lot of manipulation of polynomials and exponents that are compact valued polynomials. And so, it can be done. In fact, in the book they do it, but they don't. So, what's the solution look like? We've seen over and over again. So we're going to take all that time equals 0 at 42.
Two Gaussians. Did you do it because it's an f inverse? So you did this
And
one.
this single concentration of stuff.
So this one would be if you
We're
have
finding f omega.
And then you get broader and broader.
So this is a
But you're also getting this thing broken down by the e to the negative
inverse.
beta t.
And so all
That's
of them have
causing it
work
to
up here.
get faster and faster. So the area under this curve is decaying. It's actually there's stuff that's actually disappearing here. Okay, thanks for saying like.
And use the shifter here. This would integrate that.